Alright, so final section of chapter 9. Here's basically what's going to happen, guys. This whole idea of the power series, it's very important. Remember that the calculator is not able to compute all of these values for you without the use of one of these series, right? So whoever programmed the calculator found this power series, and then there's an algorithm that they put into the calculator, and they're able to then compute things such as sine of 0.1, sine of 3, etc., right? So there's got to be a way for us to find a power series for functions, right? So that's what we're going to do today. We've been doing that from section 8, section 9, like you literally did on the skills check today. I gave you a function and you found a power series. But we're going to find basically, I'm going to give you a general procedure to find a power series. In other words, a little bit more easier. Cool? And that's going to be through the use of Taylor polynomials, which we've already studied. So what we're going to do with those polynomials is we're going to make them into series. So refresh my mind. Remember that a Taylor polynomial takes in the form of like f of c plus f prime of c times what? X minus c over technically 1 factorial, right? Plus f double prime of c times x minus c square over 2 factorial. So technically is f to the n derivative, evaluated at your center, times x minus c to the n derivative over n factorial, right? That's what a Taylor polynomial is, right? You stop at your nth derivative. Agreed? Well, if we want to make this into a series, we can't stop. We have to continue to go to infinity. So my question to you is then, are you going to be able to find an infinite series for any type of function? No, you're not. Why not? Not that it's not continuous, but like, for example, a polynomial is continuous, but are you going to be able to find infinite amount of derivatives? No, you're at some point going to have to, it's like literally going to go to 0 and there's nothing you can do, right? So really what this is going to work for is for transcendental functions. Do you guys know what those are? Like sine, cosine, like all those trigs. Like remember, like think about it. The derivative of sine and cosine, like you'll literally just go in a loop forever, right? What else? What other functions could you think of? E to the x. Anything else? Natural logs, right? Like the logs will continue to just go on forever. And if you think about it, the derivative of natural log is 1 over x, and then after that there's no longer a natural log there, but it still gets on forever. So could I also say rational functions then? So anything is like 1 over x per se, and then just keep going forever. Cool. So those types of functions we're going to be able to represent by a Taylor series. Anything else, there's actually not a need to get a Taylor series. We can compute those things. The calculator can compute it just by literally doing arithmetic. Cool? Alright, so what we're going to do here is we're going to try to create a series based on this. There is one major flaw with what we have here, and that was the problem that Taylor and Maclaurin were running into. How could we make this work? Well, if you think about it, they were like, okay, we can try to make this into a series simply by saying from going 0 to infinity of what we have here, right? What's the flaw in here? The derivative. Because for a series to work, we should just be able to plug in values, right? And we're not going to be able to do that because we're going to plug in a value, but that's going to tell us, hey, go and find the 5th, the 10th, the 20th, the 30th derivative. So that's still leaving you to like do some side work. Do you see what I'm saying? So they went straight to here and they're like, okay, there's a problem here. We got to figure something out. Okay? So I'm not sure exactly how long it took them, so let's pretend that this is the process that they went through. Let's do an example and see how they eventually came up to discover a shortcut for this. Cool? So they saw that this wasn't going to work, so let's just try an example. Let's say that we're going to find a Maclaurin, and we're going to do a Maclaurin to keep things easy so that the center is at 0 for the following. We keep using sine of x, and I'm going to continue to use sine of x because of the whole idea that it's very cyclical. Cool? So the first thing we're going to do is forget the idea of the series for the moment. I just want to find a Maclaurin polynomial. Cool? I'm not going to tell you what degree because I want you to recognize a pattern. So we're going to find a lot of derivatives here. So let's do about 7 or 8 derivatives. We can kind of create a table. So the Euler's method is not that it's related, but it was just a way I show you to stay organized. So it's very similar. It's just a way of staying organized. Cool? All right. What's the derivative of sine? Cosine. Negative sine.
And you're done.
And I'm done?
I mean, negative cosine.
Okay.
And you're done.
What do you mean I'm done?
Now
Oh, okay. I was like, what do you mean I'm done? Okay. So now I'm back to sine of x. Fifth derivative is cosine of x. Sixth derivative is negative sine x. Seventh derivative is negative cosine x. And actually, let's just stop there. Cool? Hmm?
you can read it.
Mm-hmm. All right. So what did you do after you found derivatives? You plug in your center, right? So what's f of 0? Sine of 0 is 0. 1. 0. Negative 1. 0. 1. 0. Negative 1. Do you guys agree? Okay, and then once you found those numbers, what would you do to figure out the Maclaurin polynomial? Plug it all into this idea here, right? Now, for us, C is represented by the number 0, right? Our center is 0. So, what would it look like? Do not include anything that has the zeros. There's no point of us writing it, right? So, the very first term is the one with the first derivative, which means it's the one with the first power, right? So, the very first term is what? Literally just x. Cool? Am I going to have an x squared term? No. Am I going to have an x to the third term? Yes, I am. X to the third. What's the number in front of it? Well, a negative 1. And the third power of 3 is over 3 factorial. Okay? So it's going to be minus 1 over 3 factorial. You with me? And then what will be the next one? X to the 5th over 5 factorial. And then the next one? X to the 7 over 7 factorial. Now, do you recognize a pattern? Can you continue the pattern without finding more derivatives? What will be the next two? Minus. And then this continues forever, right? The idea here is that we want this to continue forever. We want to make this into a series. All right. So here's what they did. Or I'm assuming this is what they did. They kind of ignore this whole idea of the derivatives for the moment, and they're like, okay, do you see how I have a sequence, because I have a pattern going on here, and I have it into a series because it's being added, right? That's the idea of the series. So what we're going to do is we're literally just going to observe this and try to come up with the rule ourselves. So we're going to make a series using this. Anyone want to give it a shot?
X to the n over n factorial times negative 1 to the n.
So you gotta be careful because now this is your first term, this is your second, this is your third, this is your fourth. Like we're ignoring the top part. Like this is your first one, second, third, fourth, fifth, sixth.
2x plus 1, or 2n plus 1.
2n plus 1. Why?
So that you can get it odd.
We're gonna make the first term 0. So if we make the first term 0, I can use what you're suggesting. This whole idea of the 2n plus 1. Well, 2n plus 1, if we start at 0, would get you what? 1. Then if we go to 1, it gets you a 3, and then a 2 gives you a 5, and then a 7, and then a 9. So could I say it's 2n plus 1 factorial? And that also helps you with x to what power? To the n, 2n plus 1. Now the whole idea here is that I'm going from positive, negative, positive, negative. So it is going to be alternating. And we know that to make something alternate, we need a negative 1 to some power. Well, what specifically would it be? We'll try it. So the first one needs to be positive and then negative, positive. And we're starting at 0. So anything to the 0 power is going to be positive, right? It's going to be 1, right? Anything to an odd power is going to be negative. So could I just say n? Because 0 would be positive, 1 would be negative, 2 would be positive, 3 would be negative, and so on, right? So they're on to something. They think, or at this point we think, that this series right here represents what? Represents sine of x. You with me? So the question is, remember how this whole idea of a series, it all depends, using a series of where our center is? Because we can use it as long as we're close to the center, right? But then it becomes pretty pointless after you get out from that center, agreed? So we got to check basically how good is our series. We got to find our interval of convergence. So this is literally what you just did for me on the skills check. So how would I go about finding the interval of convergence for the series that we found? We're going to use the ratio test here. Cool? So I'm going to say the limit as n approaches infinity of the absolute value of -1 to the n plus 1. If I plug in n plus 1 for 2, n plus 1, what do I get? 2n plus 3. All over 2n plus 3 factorial. And remember, the ratio test basically tells you to take the ace of n plus 1 term over the ace of n, which is going to multiply by the reciprocal. Alright, are you guys good so far? I know you're lost, dude. Sorry. Like, this is something that, is this something you missed? Oh, okay, so like when I plug in right here on the 2n plus 1, I'm literally going and say, remember you're plugging in the n plus 1 term? So when I do that, I get 2n plus 2 plus 1, so I get the 2n plus 3. Cool? Sweet. Alright, so I'm going to get this out of the way. And here's what it looks like so far. So now I just got to use algebra. We got to be pretty good at algebra to make sure we can clean this up. What things cancel out? What am I left with? Okay, so I am going to be left with a -1, but can I go ahead and get rid of it since I have the absolute values? So technically this whole -1 idea is gone, right? I'm going to be left with an x squared because look, x to the n plus 3 is equal to x to the 2n times x to the third. Which I can do the same thing down here and say that this is x to the 2n, x to the first. The x to the 2n's cancel. X to the third over x to the first leaves you with an x squared. Cool. 2n plus 3, 2n plus 2, because the next one will be 2n plus 1 factorial, and then it cancels that out. So you're left with that. Agreed? Alright, now remember, we're not dealing with x right now. We're taking the limit as n approaches infinity. What do you get? 0. So what does that mean about the radius of convergence? So what does that mean about the interval of convergence? Okay, this is very exciting. I know you don't think so, but it really is. And I'm going to be honest, like if I was this Taylor guy or this Maclaurin guy, I would be super happy because guess what? You just found a series that represents the function of sine everywhere. Everywhere. Like it doesn't matter what you plug in, you are going to get an answer for it. So let me kind of show you on the calculator like how powerful this series actually is. Okay? So let me show you real quick what we really just found out. So the calculator knows this algorithm already, so let's just kind of, I'm going to show you with the calculator. First of all, let me make sure that I am on radians. So let's say that we want to do sine of, pick a value, I don't care. 1.7. So we plug that in and that's what we get. I'm going to use this idea of the series that we found. So this series right here. And for x, I'm going to plug in 1.7. You with me? Okay. So I'm going to do a series. Now I'm using an 84, so I'm not going to be able to put the infinity symbol up top. You with me? So I'm just going to put some number up there. Are you okay with that? So I'm going to start with x starting at, according to your ours, it starts at 0 and then it goes to infinity. So I'm going to start at 0. And believe it or not, I'm not even going to put a very high value because I don't want my calculator to be thinking forever. I'm just going to put a 10. Cool? If I plug this exactly how I have it, so let's do -1 to the x power times, well, we're plugging in, what did you say we're plugging in? 1.7. So 1.7, bless you, to the 2x plus 1 power, right? Over 2x plus 1 factorial. The factorial is under math. If you go over to probability, it's option number 4. So let me make sure. Did I type it all correct? Yes? And look at what we got. It's literally the exact same number, even though I'm not even using infinity. We found like a really, really good series. In other words, we found the series that represents sine. This is the series that your calculator uses to compute anything for sine. That's literally what we did here. Okay? Yes?
Well, what about like sine 2x or sine?
Oh, that's a very good question, which I will get to here in just a minute. Cool. So.
Is that because it has to the 10 places and you just...
So that means that I literally didn't even need that many terms to get the exact thing. You with me? Like, it ended up being really good. And then, I'm going to be honest, I tried this before making the video. I put like 1,000, and it took forever to compute. Okay? Yes?
So, when you use the ratio test here, were you just checking to make sure that the original series you had was...
Convergent, because remember, I actually failed to mention one thing. Remember, for the ratio test to work, your whatever has to be less than 1. So, it doesn't matter what I plug in. I'm going to get a 0, which is less than 1. So, that's how I was able to determine that the entire number line was going to work for us.
So, the series that we're looking at is the alternating series, -1 power n, x power 2, and all that stuff.
Yeah.
We're just down there.
Correct. Yep. We're good? So, here's basically what's going to happen, and you're not going to like it so much. What if instead of finding it every time, we could just memorize it?
Yeah, I like that.
And that's really what's going to happen here. Because look, you can sit here and just do this entire process, which didn't take us 5 minutes. It could take you a while, right? What's going to happen, guys, is, you know what? These have already been found. Like, I can sit here and we can do one for cosine, and we can do one for e to the x, and we can do one for all the ones that we mentioned earlier, but it's already been done. You see what I'm saying? I just wanted to show you what the process was, what the thought process was here. What's going to happen here is you're going to have to memorize this. So let me go ahead and reflect them for you, and you need to write them down. Cool?
How far are we going? Are we going to like part 10?
No, I'm going to give you a list here of the textbook, and I want to tell you which ones to write. Okay? I don't feel like writing them all out, so let me just go ahead and show you. Here we go. All right. Anything that is highlighted, you need to have memorized for the AP exam. So, I mean, I have them all because they're my notes, but you don't really need the first one. So, for example, we talked about the whole idea of a rational function. So, this one of 1 over 1 plus x. Here's what it expands out to look like, right? So, if we went through the whole process, derivatives and plugging in, et cetera, it goes like 1 minus x plus x squared minus x to the third plus x to the fourth. So, do you notice a pattern? So we got this idea of a -1 alternating. You with me? And then it's just literally x to the n power, right? 0 power, 1 first power, second power, third power, fourth power. So this is what it would look like, right? Now, I went ahead and did everything, whoever did it, and they found out that unfortunately for this one, the interval of convergence is only -1 to 1, and you need to know that. So that means that if you want to find out, for example, what 1.7 is, what are you going to have to do? Change the center of this thing, and then recompute all of this. Okay? Here's the one, actually, you do not need to know what ln of x is. My apologies, I thought you did, but you do not need to know what ln of x is. Here's e to the x, here's sine of the x, here's cosine of x. I'm going to go ahead and pause the video, copy everything down. Not just the rule, guys, copy down the pattern, because they like to ask questions where they just give you things with a pattern, and you need to recognize that that was sine, or that was cosine, or that was e to the x. Cool? So just copy down the ones that are highlighted, except for ln of x. If you're really interested and you want to write the rest of them down, you're welcome to do so, but your only need for the AP exam was highlighted. Cool? Alright, so I'm assuming you've already wrote all of those down. So what's the point of knowing them? Well, now we're going to be able to use them. So you asked me earlier, what if it was like sine of x to the third power? Well, let's try it. So we can say f of x equals sine of x to the third power, something like that. You with me? Because we're running out of time, I'm not going to go through the process, but I was going to have you do all the derivatives. And I want you to think this through. Right now it's a chain rule, right? So you would do a chain rule. And then you're going to have to take the derivative of that, which would be a product rule with a chain rule. And then you have to take the derivative of that, which would be a product rule with a chain rule and another chain rule. And that's just 3 derivatives. And didn't we need like 7 or 8 to see the pattern? Luckily for us, here's what we do know. We can do the following. It's going to seem silly, but it's completely true. We can let u be x to the third power. And then we can say that f of u is sine of u. And you already know what the sine of u function looks like. I mean series. What does the series of sine of x look like? Negative 1 to the n, x to the, well, I'm going to use u since I'm using u right here. U to the 2n plus 1 over 2n plus 1 factorial. Right? Now, I'm going to be honest. This will be an FRQ question. Like literally something like this. You have to mention this before you go to what I'm about to do. If that's what sine of u is equal to, therefore, what do you think sine of x to the third is equal to?
All of that, but
You literally is the exact same thing, but you're going to plug this into u. So if I plug that into u, what happens when you have a power to a power? So what would be the result here? 6n plus 3 over. And that would be the series that represents sine x to the third power. Cool? This could be very easy if you know the series. If you do not know the series, you're going to have to do all those derivatives, find out all those coefficients, try to figure out the pattern on your own until you can get here. Cool? So I'm going to be honest with you. If you were taking this AP exam, if you didn't know it and this was a multiple choice, this would be one of those that I'm skipping. Because I'm not going to, like, that's too much time that you would be wasting on this question. I would be moving on to something else. If you had time, then maybe attempt it. Cool? Alright. I want to give you one more for you to try, and then that will be our lesson for the day. Cool? So let's say that I ask you to find, I don't know, find a power series for f of x equals to cosine root of x. I'm going to go ahead and pause the video and then I'll go over it. Alright, so go ahead and check your answer. So the one that would represent cosine of root of x would be this series right here. Okay? If you're watching this video, there's technically more things that you can do with this series, but as far as my class, this is all we need to cover. So, thank you.